All right, so let's examine something I talked a little bit earlier about, which is the depth profiling. So let's look at that a little further. So we use the ion gun, right, to do this. Um, those ions typically argon, so it's a the source is basically we have argon that becomes charged, so we have argon plus. Um, we bombard the sample with that, and then those charged ions basically collide with the surface and dislodge atoms, ions, and clusters from the sample. We use that to clean the surface, but we can also use that to remove material from our sample. And so the idea here is that we sputter, to clean the surface, and then we obtain an XPS scan, so like a survey or particular regions, uh, carbon, oxygen, phosphorus, any of those regions, and then we sputter again, and we then cycle through this. We go through this process of sputtering and then obtaining a scan, and then sputtering again and obtaining a scan. And what that's doing is it's going further and further into the sample, and so we're able to, with the right conditions, based on our sputter conditions, what the current density and energy is and how long that we sputter, we're able to translate that into a thickness, and therefore we're able to get a composition as a depth from the original surface. And so that's what the composition depth profiling is. And so that's possible with XPS and AES when we're using this ion sputtering gun. So just to kind of give you an example, this is actually some results that I was part of as well in my group back in grad school. So we had this organic hybrid polymer solar cell. So we had lots of different layers. So the base substrate was glass, and then we had some ITO. On top of that, another layer. Then we had titanium dioxide. Then we had an interface between the titanium dioxide and a polymer. And then we had another interface with the metal electrode on the top. And so this is kind of the what we had. And so there was different metals on the top as well. And so we were able to, using depth profiling, right, sputter and then take scans, we're able to kind of evaluate these different interfaces. And so that's kind of what this is showing here. We have intensity, and we're looking at a lot of different elements that's tied to these different layers, and we're able to do that. One thing you'll notice here is that we have sputtering time. Because each layer is quite a bit different, it's hard to get a depth when all these, because the sputtering layer is dependent on the material. So the sputtering rate for the metal is much different than the sputtering rate for the polymer. And so that's why it's plotted in sputtering time instead of thickness. But if we know all those different values for these different layers, then we could in fact get a sputtering, a depth and a rate from this sputtering time. But you can see here that we actually sputtered for very long periods of time, basically an hour of just sputtering, and that's quite a bit. Again, so here kind of going back to the idea of how much sputtering you do. So there's a lot of variables here. So how long you sputter, and then also the conditions of the gun, so voltages and so forth. And so those rates change depending on the material. So if we have a very uniform material, so if this is just like a silicon wafer that's very uniform, then the sputtering yield, the number of atoms that it's ejected by the ion, is going to be very consistent. And we can determine what that yield is for that material and translate the time into a rate and therefore get a depth. However, if you have a very mixed sample, like the one I showed you here, with all these different materials, that sputtering yield is going to vary drastically. And so it's much harder to obtain that type of definitive sputtering yield. So the other thing that a couple other kind of things we have to watch out for when we look at depth profiling is that it can be affected by what we call preferential etching. So these areas here that are preferential etching. So if we have again a non-uniform sample, uh, different regions are going to etch at different rates. So this could be an element with a much larger sputtering yield, so more atoms are released per unit of time as opposed to the other portions. And so that can give us preferential etching. Kind of the same principle we use when we etch metallographic samples to expose grain boundaries. Same idea with that. The other thing that we have to worry about, and this is a particular problem in this example here with these different interfaces, is that there's an interface issue, and it's called interface smearing. And what that does is we have these ions, and we always think about the ions ejecting those atoms. So in the diagram I showed you here, so it ejects atoms and ions and so forth. But these high energy ions, these argon ions, can actually push ions further into the material. And it kind of smears the interface. So if you have a very smooth interface between these two materials A and B, the incident ion beam can actually push atoms of A into B because it's just colliding around this material. And so you can end up getting a different kind of profile than what you should. And so the smearing phenomenon is something that we also have to consider when we do something like depth profiling. So it's a very useful technique, but there are some things that we must consider when we do this technique.